Oh yes, so we are live. We are live now. So okay, so let's understand the DLQs, shall we? Okay, I'll just share my screen. Yes, it's visible. All right, we don't want to focus much upon the decorations of how the lighting is and all. So just focusing on the topic, we are uh, going to explore and understand together using dead letter queues in Amazon SQS. So basic purpose of live streaming is to understand what are DLQs. Now the motive behind understanding DLQs is uh, we are building it as a component. It's actually a component of a bigger project, which is nothing but a middleware that we are using to limit the traffic, we can say, between two services. So let's suppose we have a service A and service B, and service A is hitting or pushing in thousands or lakhs of requests and at service B, but service B is unable to cope up with that many number of requests versus the processing time. So basic thumb of rule of thumb is that the amount of requests that you are intaking should not consume more time than you are processing it, or else it would the buffered request would eat up your RAM, and if it eats up your RAM, then RAM goes up and up and up, and eventually there will be a point where the RAM will get 100% utilized and the system will crash. So our basic purpose behind this middleware is to control that flow and possibly fail faster, fail safer. That's the main motive behind this middleware. And obviously, this dead letter queues, which we'll see in a minute what it is. So let's go together exploring. Let me just once check if I'm live. Yeah, we good. So, all right. So, dead letter queues in Amazon SQS. Uh, Dead letter queues supports that which source queues can target for messages that are not processed successfully. Okay. DLQs are useful for debugging your application because you can isolate unconsumed messages to determine why processing did not succeed. All right. For optimal performance, it is best to keep the source queue and DLQ within the same. Yeah, correct. Makes sense. So suppose you're capturing all the requests inside a middleware and shooting streamlining basically the requests one by one in a queue, and some of them are not uh, successfully responding, they're failing. So what you'll do is you'll park them into a dead letter queue, uh, which basically signifies that this request has been dead because of XYZ reason. Right. So uh, now there's one thing key, this request will land in dead letter queues only after a certain number of retries. Okay, so let's say there is a request A, which probably due to some XYZ reason has failed and returned a failure response to our middleware. Now, our middleware will try X number of times. If it and there's a count. Basically, there's a count for the cap. We can say it's capped. It's not unlimited number of retries, which will again uh, trigger a infinite loop and consume infinite all the resources basically. That's why we have capped it at certain X number of retry count, and beyond which, if the request still fails, then it will be parked in dead letter queues. Right. So that's that. And So why do we park it? Why can't we just let it go and continue to the next request? Basically, to examine logs for exception that might have caused messages to move to the red letter queues, analyze the contents, determine whether we basically profiling and analyzing why it failed. So move messages out of red letter queues using red letter queue redirect. Okay, you must first create a new queue before configuring it as a dead letter queue. Okay, for information about configuring a dead letter queue using the Amazon SQS console, see this. Okay, so using policies for DLQs. User to specify the max receive count. See, this was the thing which we were talking about. So max receive count is the number of times consumer can receive a message from a source queue before it is moved to a dead letter queue. Correct. For example, if is set to a low value such as one failure to receive a message would cause the message to move to the dead letter. Okay. To ensure so resilient against errors, set the max high enough to allow for the sufficient retries. Fair enough. For standard queues with the redirect policy, where X is greater than 3. If a message is received 3 or more times without being detected, SQS moves it to. So I suppose that SQS is the middleware here, which we are trying to build, and that's what they're talking about. So SQS moves it to the back of the queue. The approximate age of oldest message metric then reflects the age of the next message that hasn't exceeded this threshold. Okay. The approximate age of oldest message metric then reflects the age of the next message that hasn't exceeded this threshold. Okay, so basically they're talking about if certain number of requests, how do we track if it's easier if we can uh, if we have only one request that is failing, but what if there are multiple requests that are failing? How do we keep the track of them and how do we retry it based on the retry count? So each, assuming there are n number of worker threads, each worker thread will update the count for that particular request. And basically, I'm thinking of let's say we have a pair of counts, the request ID, or basically the request endpoint, uh, versus the what do you say, uh, the count or the last message timestamp basically, and based upon that, okay, that is one approach I can think of. Okay, let's read further. I will park that for the later. The reader allow policy specifies which uh, source queues can access the red letter queues. We can choose whether to allow all source queues, allow specific source queues, or deny all source queues without dead letter queue. The default allows all source queues to use the dead letter queue. Okay. If you choose allow to specific queues using the Y queue, you can specify up to 10 source queues using the source queue now. All right. That's too depth, I would say. Understanding message retention periods for dead letter queues. Okay, let's try to understand this particular block. For standard queues, the expiration of a message is always based on its original in-queue timestamp. Okay, When a message is moved to a dead letter queue, when a message is moved to a dead letter queue, the NQ timestamp is unchanged. All right. The approximate age of oldest message metric indicates when the message moved to a DLQ, not when the message was originally sent. All right. So, so after trying n number of times, assuming n to be the max cap of retries, after n number of tries, you will move the request at time t in the DLQ. So, assuming that a message spends 1 day in the original queue before it is moved to a DLQ. If the DLQ's retention period is 4 days, the message is deleted from the DLQ queue after 3 days and the approximate is 3 days. Thus, it is best practice to always set the retention period of a DLQ to be longer than the retention period of the original queue. Makes sense. For FIFO queues, NQ timestamp resets when the message is moved to a DLQ. The approximate age of oldest message metric indicates when the message moved to DLQ. In the same example above, the message is deleted from the DLQ after 4 days, and the approximate age of oldest message is 4 days. Okay, so what is this PDF? Let's click. Meanwhile, let's also check the second page. Okay, so let's configure a DLQ using the Amazon SQS console. Okay, basically this is the internals of a simple queue service. All right, it's great. Actually, we can refer this. If we read the index, what it is saying. So, what is Amazon SQL? Getting started. Okay, creating a queue, managing a queue, standard queues, at least once daily, before queues, quotas, features and capabilities, DLQs using policies, configuring Amazon SQS, best practices, Java SDK examples. Yeah, we can refer this using APIs. We can refer this for more info. Yep, we can definitely refer. All right, so that's that. I think we have got a brief idea of what DLQs is, and yeah, I think we're good to go now. Let's end the stream here.